Okay, everyone, let's continue. So far we understood why do we need to use the proportional controller or PI controller, proportional plus integrator controller. As we saw from the example, we can improve the performance of the first order system well using the PI controller because we can work with two damping ratio and natural frequency of the system. But if we have the second order system, we can't deal with the all coefficient of characteristic equation. If steady state response is enough for us, PI most probably is good. But as we saw again from the example, integral controller can add overshoot to the system. So we need to somehow deal with it. So we can use the derivative controller as well to add 1 degree of freedom to our control system design as a PID controller. What's the advantage? First, if you look at the PID controller or PD controller, if I have a PID controller, I have 3 gains. If I have just PD controller, I have KT and KD. As I said, TI we can call it as the reset time and TD derivative rate. If I use the derivative part, I can improve the stability of the system. The derivative part makes the system more stable, reduces overshoot of the response. But in theory it's good, but in practice we can't use the derivative controller. Or if we want to use the derivative controller, its gain should be small. What's the reason? What's the reason?
Because it introduces the S.
Okay, S is the derivative. So what's the drawback of using derivative control in practice?
It reduces the type number of the system, so it reduces the.
No, SADS error, derivative error in any ways can deal with the SADS error. It doesn't affect at all on SADS error. Why it can affect the SADS error or type of the system? What? No, because we have KP plus KDS. If we multiply the transfer function of the Planck, KDS is always in the denominator. Okay, so it doesn't affect any type of the system. The type is the number of integrator in denominator. So it doesn't affect the SADS error in any way. The reason is that, look, if assume I have just the derivative as an assumption, KDS, Planck GS, feedback error, R minus plus 1. Assume in my feedback I have a very high frequency noise. For example, noise N, okay? 10 times less than. So for example, 2 cosine 100 t. Okay? Or let's say N equal to 0.02 cosine 100. Very small amplitude but high frequency. If this error or this noise comes to the controller gets a derivative of this value. What would be the derivative of this one? N prime will be 0.02 multiplied to 100 sine 100 omega t. It's 100 t. Look, the amplitude will be magnified 100 times. So if I have even very small noises, it will be magnified highly by, significantly by derivative controller, which damage the performance of the whole controller. This is one way of the reason if I have very high rate change of the input, for example, sawtooth input. This will be the derivative, the integrator, the derivative part will be take the derivative of this slope, which is infinite. Again, damage the system, the response of the system. If I have the smooth input, is fine. But if I have a random input with the high change rate, it will damage the response of the system. So we have two drawbacks. When, first, it magnifies the noises of the sensor. Second, it can deal with the high rate change of the input signal. But with the small gain of the derivative, I can improve the overshoot and dynamic response of the system. But again, it shouldn't be too much compared to the integrator and proportional gain. Again, derivative control typically makes the system better damped and more stable. However, the effect of the derivative control term depends on the rate of change of the error and the noise sensor noise. So, as a summary, wrap up the PID controller. If I just use the proportional controller, in general, rise time will be decreased, which is unwanted usually. Overshoot will increase, which is unwanted. Settling time, a small change. Steady state error will be decreased, wanted. Stability will decrease, unwanted. It is very general. It's not correct for the all cases, but in general, this is the performance. Ki, rise time decrease. Sorry, rise time decrease is wanted. What we want. Overshoot will increase, which we don't want it. Settling time increase, we don't want it. Steady state error will be eliminated. Perfect. Just a moment. And stability will decrease. Yes.
The steady state error decreasing with KP, is that the
Decrease.
steady state error will get lower as you get a higher gain?
No. Look, as I said, it's not a general case. If you look at the example I ran for you, MATLAB code, if I just use the proportional control, the steady state will be increased.
Yeah.
Okay, but because it wasn't well tuned. If you well tune it, you can decrease the steady state error using the proportional control. Decreasing means that absolute value of the error goes to zero. Doesn't matter, it's negative or positive.
And you can only do that when it's written into it.
It's what?
You can only eliminate steady state error when it's
If
written into it.
if I have just integrator. Okay? Look, in terms of the well tune, in some cases you can, for example, design the KP which had the zero steady state error. But for sure, the dynamic response has been damaged completely. We are talking about the good design. The conflict, the trade-off between the conflict requirements. If I want to have the good rise time and decreasing the steady state error, I can improve it, but I can make it zero. In very special cases, this is possible. But in general, for the diverse range of the system orders, it's not possible. This is the case. If you use the derivative controller, rise time slightly will change, but not much. Overshoot for sure will be decreased. Settling time will decrease, which is wanted. No effect on the steady state error, as I said, because I have KDS will add a zero to the transfer function. It doesn't appear on the characteristic equation. And improve if KD is small, stability. If I increase the KD, for the large KD, for sure it will affect the stability of the system in terms of the noise magnification or change of the input rate. So hopefully you know now what we use the PID controller and how we can design a PID controller. Or when do we need to use P controller or or PI controller or PD controller or in general case PID controller. Again, let me show you another example. Hopefully the speed is okay. I don't think so. Okay, but I recommend you go home and try to apply different input to this MATLAB code and see how the response will change subject to different inputs. But here again, I have the step input for the second order system. I have a second order system here. Okay guys, till this one is running, I want to make the module a little fun. Do you want to have a competition?
Yes.
Yeah? So, by tomorrow morning, by tomorrow morning, I want to know. The look is optional, is not mandatory. We will have just one winner, not everybody winner. I will give a 100% word to the winner, just to the winner. In one page, explain clearly to me. How can I design a PID controller or PI controller using what the old things that I have I told you so far. What I have taught so far, I told you how to use the rise time, settling time, for locations. I talked about the SSD error, final value theorem. I talked about system type, everything. You need to clearly tell me how we can use these topics or these definitions in our control system designs. I want to have the overall PID control design using the old thing that I have discussed so far. Okay, in clear way. Whoever give me the most correct, accurate answer is the winner, and 100% coursework. Okay, it's up to you. Tomorrow morning I need it. Just one page, maximum one page. Maximum one page.
Just an explanation.
What? Just explanation. I don't need any formula, anything. Just explain to me how can I use whatever I have discussed to design a PID controller. Okay? I think it's fair enough to give you 100% coursework. Just 1% is the competition. The most accurate. This is the design, and I'm sure. Look, this is the design. If I see 2% give me the very perfect answer, but in different ways, for sure I will give 100%. But I need to see the perfect response.
If we do in the team, can we have 50%?
No. Just one. Just one. Okay? Just one. So by tomorrow morning at 8 a.m. At 8 a.m. As I said, I wish all of you get the A+, and I will do my best for all of you to get A+, or at least 100. But it depends on you as well, your performance. If I get the perfect explanation of the course material so far, PID design, I think that guy here deserves 100%.
Like whoever gets this, can they give their 40% that they already have?
No, it's vision, 100%. If you are right for me. If you're fine with 30%, okay, it's up to you. But still, you need to do your coursework to get the rest of the mark. Okay, so it's up to you. So, it's still running. Right, it should be clear. Everything should be included in your explanation. Whatever I have talked about this so far. In clear way, how we can use those to design a PID controller. In one page. Okay, if you look at the response of the system, a second order system to a step input, system without controller, as you see, we have the oscillation, high rise time, overshoot, very high settling time, a steady state error. Perfect, we have everything. If I use just the proportional controller, which means Ki and Kd are 0, I can improve the steady state error, I can improve the rising time of the system, but look, the damping ratio has been decreased. And I have a lot of oscillation, very oscillatory system or response. If I use the PI controller, Kd0, again, a steady state goes to 0. If it is completed, it will be 0. Rise time is somehow improved, but settling time is damaged, increased. And I have still a lot of oscillation. If I use PD controller, overshoot is reduced, rising time is improved, but I can't do anything with the steady state error. If I want to improve steady state error, reduce the damping ratio, reduce the oscillation, improve the rising time, PID controller. Look, the overshoot is almost 0, steady state error is 0, very fast rising time, and that's it. This is what all I wanted. This is so slow, I can't run for the other type of the inputs, but please try this MATLAB code for the sinusoid input, for the sawtooth input, for any other ramp input, any other type of the inputs, to see how the PID controller can improve the the overall response of the system. Okay, so how, look, when I have the PID controller, I have 3 gains. How can I tune gains practically, not mathematically? What I ask you for this competition is the mathematical, theoretical design of the PID controller. What I'm telling you here is the practical tuning of the PID controller, gains of the controller. In reality, the closed loop transfer function, the closed loop response is in the form of the first order system, as you saw from the MATLAB code example. This first order system can be divided in different sections. The first section is lag time. What's the lag time or dead band zone? Or delay, what's that? Is the time takes the system to respond to input. If we have very fast response, we have almost 0 lag. But if we have the slow response system, we have the system needs some time to react to the input to the system. We have rising time tau and the steady state error. final value of the response. If we assume that the response of the closed loop system, which is in most of the cases, is in this shape, we can tune the Kp, Ki, and Kd using this table. First of all, we can estimate the closed loop transfer function ys or us as the a e minus std. E minus std represents the time delay, tau s plus 1. The optimum gain, if I just want to use the proportional controller, is 1 over RL, which R and L is defined in the previous picture. If I want to use the PI controller, the Kp is the 0.9 over RL, and Ti is L over 0.3. If I want to have a PID controller, it's better to choose the gain of the proportional controller as 1.2 over RL, and Ti equal to 2L, and Td equal to 0.5 L. Okay? Do you remember this, Nicolas Ziegler? From the year 2 control module. Okay, so I will close the chapter of feedback control system in Laplace domain, and from now on I will start working explaining on the state space form or state space control system design. As I discussed in the first lecture, we have 3 types of working with control system design: Laplace domain, frequency domain, and state space domain, or time domain. We talked about Laplace domain, and you learned somehow from the year 2 control module. Frequency domain, you know somehow from year 2 module. I wanted to talk about the frequency domain as well in this module, but unfortunately we don't have time for that. I spent a lot on the control design in the Laplace domain and this space domain, so we don't have time to. I wish I could teach you the frequency domain as well. But as a fundamental, you have enough background in terms of the frequency domain from the year 2 module. But the topic of the state space method is totally new to you. You haven't heard so far using the state space method. Laplace domain or frequency domain control design they are good, but for a very simple system. That's why we call those control system design the classical controller. The PID controller, classical control design. The classical controls, to be honest, we call it the state space method as a modern control system design. It is started developing from 1950. It is not that much new, but compared to the classical control system design that started from the 18th century or 19th century, is much newer compared to that one. Again, PID controller are good for the very simple control systems or very simple system which we have just one output and just one reference. Or we have the very low order differential equations, system equations. But nowadays, for example, suspension system, the coursework you have, or other control systems are very complicated, and they include many high order differential equations. So it is much easier to use the state space format to design the modern control system or complicated control system. How does it work? I will explain to you. In state space design, the control engineer design a controller by working directly with the state variable description of the system. What's the state variable description? Again, I will explain to you today. Again, in many modern systems, we have multi-input, multi-output system. We don't want to just control one part of the response. We want to control different responses at the same time. For example, using the PID controller, you can just, if you have the dynamic system, you can just control the position response of the system. What happens if I want to control at the same time position, velocity, and acceleration of the system? In this case, I have 3 outputs and I need 3 reference inputs. 1 reference input for the position, 1 reference input for the velocity, and 1 reference input for the acceleration. So I have 3 outputs, 3 inputs. PID control or classical control system can deal with such systems, but very hardly, and is not easy to work with them. At least they are not computer version of the control system design. Nowadays, with the control system design, we need to have a methodology or method to develop the control system using the computers. State space format is a very suitable approach to design the systems, control system using the computer. As I said here. Okay, but another advantage of the state space formulation is that we can reduce or we can transform the high order differential equation to the first order differential equation. Always working with the first order differential equation is much easier than working with higher order differential equation. For example, second order differential equation compared to the first order differential equations. So the big advantage of the big benefit of using a state space format is that we transform higher order differential equations to the first order differential equation. How we can do that? I will explain to you. But in general, why is it convenient to write equations of motion in state space format or form? Here. It provides a standard way to describe the differential equations for any dynamic system, for any complicated dynamic system, so that computer-aided analysis can be carried out more conveniently. Also, it is more convenient to analyze linear system in terms of the standard description matrices in the state space format, because it reduces the higher order differential equations to the first order differential equation. As I said, the motion of any finite dynamic system can be expressed as a set of first order ordinary differential equations. Again, the Laplace transform, so far we just discussed about it, is just work for the linear system. But using the state space formulation or format, we can design the controller for the highly nonlinear system as well. So we can easily deal with time varying, nonlinear system or any kind of the complicated system. But what I will talk about it here will be for the time invariant linear system. But keep in your mind that you can easily deal with the highly nonlinear time varying system using state space formulation. Let me explain this one by an example. Cruise control model. We have a car, and we want to design a cruise control for this system. The first step of any type of the control system design is what? Equation of motion. Exactly, equations of motion. So I need to build up equations of motion. What's the output here? What do I want to control? Speed. And what's the input? Engine power. Exactly. Or I represent engine power as the control action U. So I can represent or model a vehicle for the cruise control system using this very simple mass system. I have a mass, external force U, which is the engine torque or engine power, and I have a friction force Bx dot. So the equation of motion using the Newtonian law is the U minus Bx dot equal to Mx double dot. Or in other words, I have x double dot equal to U over M minus B over Mx dot. look here, I have the second order differential equations. For this simple differential equation, I have analytical solution. But assume I have a fifth order differential equation. How can I solve it? There is no analytical solution for that. I need to solve it numerically. If you want to solve it numerically, there is no chance to design a control system. So how can I transform this differential equation to a state space format? I define two variables. x1 as x displacement and x2 as x dot velocity. If x1 is x and x dot 2 is x dot, what's the x dot 2? No. X dot 2. Sorry, excuse me. X dot 1. What's the x dot 1? Okay, what's the velocity here?
X2.
X2. Look, my variable is x, position, and velocity. If I this one, x1 equal to x, and x2 equal to x dot 2, it means x dot 1 is equal to x2. Correct? So, I can reshape the equation of motion in this form. X dot 1 equal to x2, and x dot 2 is equal to u over m minus d over m x2, which x2 is x dot. So instead of one second order differential equation, I have two first order differential equations. Correct? So that's the way I transform the represent or to show the equation of motion in state space format. I can rearrange this set of first order differential equation in the matrix form as a x dot equal to fx plus gu. In this module, when I show a variable as the bold on italic format, it means we have a matrix, vector or matrix. If I show a variable italic, non-bold, it means I have a scalar value. Okay? We call it x equal to x1 and x2 as the state vector of the system. And we can show the output of the system, in this case is the y, is the velocity, as combination of the state of the system and input of the system. In this case, for this one, x dot 1 and x dot 2, which is x dot, is equal to this matrix multiplied to x1, x2 plus 0, 1 over mu. If you do multiplication, you will get these two differential equations. Okay? And the output is velocity, is x2, will be 0, 1, x1, x2, 0 to x1 is 0. Plus 1 multiplied to x2 is x2. Y is equal to x2, x2 is x dot, which means output is velocity. Is that clear to everyone? If you go to the R&D control system design of any industry or any company, you will work with this modern control system design. Okay? Again, the column vector x is called the state of the system and contain n elements for an nth order system. If I have fifth order system, I have 5 states, at least 5 states, or maybe higher. But a state of the system is not just a mathematical description. It has a physical meaning. Usually, a state of the system are those system that we can measure it or had some physical meaning. In this case, our state vector is what? X1 and X2. What are the X1 and X2? Displacement and velocity. Correct? For the electric motor, for example, you can measure displacement using the tachometer and using the potentiometer, and velocity using the tachometer. Or for the vehicle, you can use the proper sensor to measure the displacement and velocity. What's the most advanced sensor to measure the velocity and displacement?
GPS?
GPS. The most accurate sensor to measure the displacement and velocity of the car is GPS. So for the mechanical engineers, the state of the system, state vector of the system usually consists of displacement and velocity. The quantity F, or the matrix F, is n by n system matrix. We call it the system matrix, the matrix F. Vector G is the input matrix. Vector H, or matrix H, is the output matrix, and J is the scalar called the direct transmission term. Usually J is 0 for the simple cases, for simple mechanical system. So the state variable method of specifying differential equation is used by computer-aided control system design software package, usually MATLAB. Using the final difference, you can solve it. Therefore, in order to specify linear differential equation to be computed, we need to know the values of the matrices F, G, H, and J. Usually MATLAB use A, B, C, and D. Different representation, but the same concept. MATLAB use the variable A instead of A, B instead of G, C instead of H, and D instead of J. Okay? If you look at the MATLAB help, all description is based on the A, B, C, D matrices. Okay, as another example, we have a DC electric motor, which free body diagram can be shown as this picture here. We want to write first equations of motion, and second represent or convert or transform this differential equation to a state space format. We have two parts because it's the mechatronic system. We have electrical part and we have mechanical part. What's the electric motor? Is the actuator what does this actuator? Convert electrical energy to mechanical energy, or electrical power to mechanical power. So, if I apply the second Newtonian law to the rotor of the motor, I will have the J m theta double dot m plus B theta dot m is equal to KTIA. KTIA is the torque applied by the magnetic field of the electric motor. Rotor, in fact. KT is the motor constant, AA is the current of the armature of the system, electric motor. And if I use the Kirchhoff voltage law, I will have the LA dt plus RA IA equal to VA minus KE theta dot m. If you don't know how to write this one, it's not the matter. I just want to see. Just wanted to show you how to convert this differential equation to the state space format. To convert this differential equation, look, I have a second order differential equation, and I have one first order differential equation. How many states do I need at least? I have a second order differential equation, so I need to have two. Yeah, exactly. I have two states to represent this second order differential equation in the state space format. And here I have the first order differential equation, so I need one state to represent this differential equation. So in total, I need 3 states. The variable of differential equation here is what? Is IA. Okay? We have the IA differentiation. And for the first one is theta m. So I will choose my state as theta m, theta dot m, and IA. Look, the differential variable here is theta m. The differential variable here is IA. For this one, I need 2 states. So I choose theta dot and theta m. And here I choose just IA. If I choose the state vector, or define the state vector as this one, theta m, theta dot m, IA transpose, because the state vector is the vector, a column vector. I can show as a transpose to compact the writing of the system. If I use this S space, I will reach to the F, G, H, and J. Here the output is the position, theta m. If I have 2 outputs, theta m and theta dot m, H will be 1, 1, 0. If I have 3 outputs, theta m, and IA, H will be 1, 1, 1. So if you do multiplication, x dot equal to fx plus gu, you will reach to these 2 differential equations in first order format. Okay? Next week, I will talk about what's the connection between state space format and the Laplace transform, and how we can check the stability of the system using the state space format, and how we can design a controller using this representation. Tomorrow, 8 a.m. 8:01 won't be accepted.